Hi there, it's Paul. I'm still recovering from my cold, but I'm going to try to tell you a thing or two about the gamma function, the gamma distribution, and the chi-squared distribution. This is pure probability, no statistics. So let's start with the gamma function. It's defined as an integral. The integral's improper because the upper limit of integration is infinity, and what we're integrating is the function x to the r minus 1 power times e to the minus x. We're going from 0 to infinity, and we have to do two other things. First, $ val, so we don't get the error estimate, just the value of the integral, and we have to vectorize the function so that we can apply it to a vector of arguments. So now I've got my own definition of the gamma function, and I can apply it to values from 2 through 8, and when you look, you see factorials: 1 factorial, 2 factorial, 3 factorial, and so on. If I apply it to argument 0.5 and square the result, I get pi. Now this integral will work for any positive x. If x is negative, it diverges. But if x is positive, it's a perfectly well-defined number. So we can plot this function from 0.1 to 4.5. You've already seen that it agrees with the factorial function when the argument's an integer. So I can put those values on the plot, and you see we've invented something that agrees perfectly with the factorial function, but interpolates it rather nicely. It shares with the factorial function the property that when you evaluate gamma of r plus 1, you get r times gamma of r. That's a translation of r factorial is equal to r times r minus 1 factorial. So, for example, if I take the ratio of 5 to 4 for my gamma function, I get 4. If I do it instead with 5.34 and 4.34, where the factorial function makes no sense, I still get 4.34 as the ratio. Now for the gamma distribution. This is called the gamma distribution only because what you need to normalize the probability density function so that the total probability is 1 is a gamma function. There is already a d gamma built into r, but I'm going to define my own and call it my d gamma. And the density function is parameter lambda raised to the r power divided by the normalization factor, my gamma of r. Then that gets multiplied by x to the r minus 1 times the exponential of lambda times x. And I am going to vectorize this so that I can make plots of it, but I have to specify that the argument for which I want it vectorized is the one named x. Don't worry about the subtleties of these vectorized functions that you define in R. Special case: if r equals 1, I get the exponential distribution. There's a plot of my gamma function. I will overlay the plot of the density function for the exponential distribution with parameter 1 in a different color. It overwrites it perfectly. The two functions are exactly the same. And in fact, this is exactly the same as the density function d gamma that's already built into R. I can check that my d gamma is properly normalized. I integrate it from 0 to infinity, and I get 1. I can plot it, and I can plot the built-in d gamma in a different color. Add was equal to true, so it puts it on the same plot and overlays my plot. That proves the two functions are the same. Now let's look at the moment-generating function, which turns out to be surprisingly simple. For a gamma distribution, you need a rate parameter, lambda, and I'll use two different scale parameters. I always have a terrible time remembering which one is called the rate parameter and which one is called the scale parameter. The rate parameter is the same thing that already shows up in the exponential distribution. It's the exponential decay. So I picked some values to use, And now I'm going to compute the moment generating function when the scale parameter is 3.2. First, I make the function that we have to integrate. So I will take the exponential of x times y times my gamma density. This is a function of two variables now, both x and y. I want it vectorized with respect to x so I can integrate with respect to y and still end up with a properly vectorized function. I integrate. Don't worry about the details of this. After about half an hour, I figured out the best way to do it was by using sapply. And there's my moment generating function. Singularly uninteresting as these moment generating functions are, we know that all the information is captured in the moment generating function, but it's certainly not apparent to the human eye. In fact, this integral can be done analytically, and the result's very simple. It's lambda over lambda minus x raised to the r1 power, and if I plot that, I get the same thing. Recall, you can always get expectation and variance out of moment-generating functions. You do it by taking derivatives, and I'm going to approximate these derivatives numerically. Take the value at two values, one of them 0, one of them a very small positive h, divide by h, and I get the value 1.28 plus change. The theoretical value is r1 over lambda. Near perfect agreement. Similarly, I can estimate the second derivative numerically, and I can compare with r1 over lambda squared. Good agreement. In other words, the formulas in the back of the textbook for the expectation and variance of the gamma distribution seem to be borne out by our own simulation. I'm going to do the same thing for r2. I'm just repeating code here, but I want to use both these moment generating functions together. Because recall, the big deal about moment generating functions is that the moment generating function for the sum of two random variables is the product of their moment generating functions. So I'll do one more. The moment generating function, now I'm using r1 plus r2, and that's what the result looks like. When I get the expectation, it is very, very close to r1 plus r2 over lambda. But now, for the fun of it, let's multiply our earlier moment generating functions together and plot the moment generating function for parameter r1 multiplied by the moment generating function for r2. And not too surprisingly, it overwrites the curve I just plotted. And furthermore, if I take lambda over lambda minus x and raise it to the r1 plus r2 power, that's another way of getting exactly the same moment generating function. Now for the interesting connection between the chi-square distribution and the gamma distribution. What we're going to do is take a gamma distribution for our rate parameter, which we've been calling r. We'll use 1/2. For our scale parameter, we will use k over 2. I've chosen k equals 3. You can rerun this script with any other value of k that you choose. And now I'm going to plot the gamma function. There it is. And for comparison, let's ask r for the density function for chi squared with k degrees of freedom. It's exactly the same. So that's the whole story on chi-square distributions. They are just gamma distributions where the number of degrees of freedom is equal to twice the parameter in the gamma distribution. For chi-square distributions, therefore, just as was the case with gamma distributions, parameters add up when we add up random variables. So let's choose three different numbers of degrees of freedom, 2, 5, and 3. There's the chi-squared distribution for 2 degrees of freedom, for 5 degrees of freedom, for 3 degrees of freedom. Note, by the way, that it's only when you have more than 2 degrees of freedom that the chi-squared distribution is 0 when the argument is 0. Now what I'm going to do is take one sample from each of the 3 distributions and add them together. And of course, I'm going to do this the usual 10,000 times. So for my sum, which I'll store away, I use the sum of 3 samples of 1 with these 3 different parameters. And I plot a histogram of the result. Theoretically, this should match a chi-squared distribution with 2 plus 5 plus 3 degrees of freedom. And what do you know? It does so perfectly. Finally, let's explore in R the connection between the chi-square distribution and the normal distribution. Here is how you make a chi-square distribution from a normal distribution. You sample from a normal distribution, but then you take the square of the sample. So I will do this 10,000 times. I will take a single sample from the normal distribution, square it, store it away, and look at a histogram of the result. You've seen that before, right? That's the chi-square distribution with 1 degree of freedom. There's a plot to show it. Now let's do this with k-samples. I've chosen k equals 6. You can use any other value if you want to. Again, 10,000 times, I will generate a normal distribution. And now I have taken 6, k equals 6, random variables, and I will take the sum of x squared. Remember what that does in R. It takes this vector of 6 elements, squares each component, and then adds the result together. So we're taking the sum of 6 squares of normally generated random variables. We plot a histogram of that. It should be a chi-square distribution with 6 degrees of freedom, and indeed it is. And that finishes up this brief summary of the gamma and chi-squared distributions, which we will use quite frequently in the rest of the course.